So, is power factor correction actually damaging our aging infrastructure? It's a really interesting paradox, and today we're going to dive right in. Let's just start with this question. What if a tool that we designed to make things more efficient is actually, quietly, making our old power grid more fragile? I mean, think about it. Under the wrong conditions, this thing can amplify harmful electrical noise. It can create what's called resonance and just pile on stress to equipment that's already getting old. This is a story about a trusted tool and, well, some pretty serious unforeseen consequences.
Okay, so to really get what the problem is, we first have to understand why we even have this thing in the first place. So let's talk about why power factor correction, or PFC, even exists. For decades, this has been the hero of the electrical grid. It all comes down to this thing called power factor. Now, the best way to think about it is like the foam on a beer. The beer itself, that's the useful working power. We measure that in kilowatts. The foam, well, it's just wasted space, right? But it's still taking up room in the glass. The total of the beer and the foam is what we call apparent power. So a good power factor, let's say over 95%, means you're getting a lot more beer and a whole lot less foam. Makes sense, right?
And you can see that right here in this classic power triangle. The whole goal is to shrink that apparent power side of the triangle so it gets way closer to the useful power side. You see, a lot of electrical equipment, especially big motors, create this thing called reactive power. PFC uses capacitors to basically cancel out that wasteful part, which means the utility doesn't have to pump out as much total power to get the same amount of real work done.
And the benefits? Oh, they are super clear. When you correct the power factor, you bring down the total current flowing through the whole system. What does that do? Well, it cuts down on heat losses in wires and transformers, it frees up capacity so the grid can handle more customers, and this is a big one for industrial plants, it can seriously lower their electricity bills. I mean, it's pretty much a win-win for efficiency.
But here's where our story takes a sharp turn. Because under the right, or maybe I should say the wrong conditions, these super helpful capacitors can create a totally new and really dangerous problem, especially in the kind of electrical world we live in today.
And here's the key thing to get. The problem isn't really the capacitor itself. Nope. It's the environment we put it in. Think about all our modern electronics, computer power supplies, LED lights, all those variable speed motors. They don't draw power in a nice, smooth wave. They kind of chop it up, and that creates all this electrical noise that engineers call harmonic distortion.
And this is where things get really interesting, because we've got a fundamental conflict. So on one hand, you've got the power grid itself, all those transformers and miles of lines. It has a natural inductance. Its opposition to current, its impedance, goes up as the frequency of that harmonic noise goes up. But capacitors, they do the exact opposite. Their impedance goes down at higher frequencies. This basically turns them into a giant sponge, just soaking up all that harmonic noise.
And that is what sets the stage for something called resonance. This is the absolute perfect storm. At one very specific harmonic frequency, the rising impedance of the system can perfectly match the falling impedance of the capacitor. What happens then? They cancel each other out, creating an almost zero impedance path. It's like you've just opened a fire hose for all those nasty harmonic currents.
So, let's walk through exactly how this happens. Step 1. All our modern gadgets are pumping out that harmonic noise. Step 2, the PFC capacitor, which is supposed to be helping, acts like a magnet and starts pulling in all those high-frequency currents. Step 3, if the system's properties are just right, we hit that sweet, or not-so-sweet spot, that resonant frequency where everything just cancels out. And finally, bam, resonance. Instead of fixing a problem, that capacitor is now amplifying it, creating these huge voltage and current spikes that can wreak havoc.
So how does this, abstract electrical threat turn into a real physical danger? Well, it happens when you slam it up against the reality of our power grid. A lot of it is old, and frankly, it's getting brittle. I mean, the equipment that is the backbone of our grid. We're talking transformers, switches, cables. It was all designed and built for a completely different world. It was made for clean, stable, predictable 60 Hz power. It was never meant to handle the messy, distorted, high-frequency chaos that today's electronics create.
So how does this actually break stuff? Well, a few ways. First, just flipping a capacitor bank on and off creates big voltage spikes, called transients. But then, resonance comes along and magnifies those voltages to insane levels, high enough to literally puncture the insulation on equipment. At the same time, all those extra harmonic currents are making things run hotter and hotter, This thermally ages the insulation, making it hard and brittle over time, which, you guessed it, just speeds up failure. Yeah, and this quote really just drives the point home. Once that insulation has become brittle, it's basically a ticking time bomb. The very next routine fault, something that systems should handle easily, creates physical vibrations that can just crack that fragile insulation, and then you've got a catastrophic internal failure. It's game over for that piece of equipment.
Okay, so this all sounds pretty bad, right? But the situation isn't hopeless. The answer isn't to just ditch power factor correction altogether. In a lot of systems, capacitors are still a vital and super efficient tool. The danger really comes from a bad fit. So the real answer, as it often is just smarter engineering.
So we don't have to throw the tool out, we just have to use a more advanced version of it, one that's specifically designed for the grid we have today. And that solution is called a detuned capacitor bank.
So what the heck is a detuned bank? It's actually a really elegant and simple idea. Engineers just add a reactor, which is an inductor, in series with the capacitor. This little addition is carefully chosen so that the whole unit still corrects the power factor at our normal 60 Hz frequency. But at those higher, nasty harmonic frequencies, it actually becomes inductive and blocks those harmful currents instead of attracting them. It basically stops resonance before it can even get started.
And this isn't guesswork at all. It's a very methodical engineering process. You have to go on site, you measure the specific harmonic fingerprint of a facility, you model how the whole system is going to behave, and then you carefully select the right reactor to tune the capacitor bank to a safe frequency, far away from any potential resonance points. It's all about context.
All right, so let's bring this all together for our final diagnosis. Because it's all about matching the cure to the specific condition of the grid you're working with. Which, of course, brings us right back to where we started. Is this supposedly helpful technology actually hurting our grid?
And the honest answer is, well, sometimes yeah, indirectly. Look, capacitors aren't the enemy here. The real problem is when we apply a simple tool to a really complex modern problem without thinking through all the consequences. They can take a system that's already weak, already stressed out by age and harmonics, and just push it right over the edge.
And that leaves us with this final thought, which I think sums it up perfectly. Think of power factor correction as a powerful medicine. When you give the right dose, it works wonders. But if you apply it to a fragile, aging patient without doing a proper diagnosis first, the prescription itself can cause serious harm. And for an aging grid, it's the dosage and the diagnosis that matter more than anything else.